Welcome to Module 6, Lesson 6.1. We're going to keep going with structural analysis now, but now we're going to move on from trusses and look at frames and machines. Lesson 6.1 Objectives. We're going to be able to construct free body diagrams of frames and machines and their members. And we're going to use the free body diagrams to develop equations of equilibrium to determine the forces acting at the joints and supports of a frame or machine. So we're going to be able to solve for reactions for frames and machines based on our free body diagram work that we're going to learn to do. So frames, first, they're like trusses in that they are used to support loads. However, trusses are very specific structures that consist only of two force members. They're always axial tension or compression members, right? They always form triangles. They always have frictionless pins at each end. They're all two force members. Every member of a truss is a two force member. Really, there's no trusses in the world, right? They're a construct of our engineering minds. Everything's really a frame. But if we can make those assumptions that define what we call a truss, it makes our analysis much easier. So we can use the method of joints, for instance, and the method of sections very easily on trusses, or at least much more easily on trusses, because we don't have to worry about any other internal force besides axial force. Remember, the two-force member assumption means that they're only going to have axial tension or compression, which is really cool for a truss. In general, we have frames. Their members can have internal shear forces and moments in addition to those axial forces, which means they're just much more complicated. So kind of by definition, frames have at least one multi-force member. Okay, and all we're saying by that is if a truss, is defined as something that's having only two force members in it, then a frame has to have like one multi-force member in it, otherwise you could look at it as a truss. So frames are just more general in nature than a truss. Machines, though, they're like frames in their statics. We analyze them very similarly, but their purpose is to redirect, modify, or apply forces on things. They're meant to do work for us, not just to support things, but to actually apply force to other things or to perform work on other things because we're lazy or productive, however you want to consider it. This track hoe here is moving the dirt into the dump truck. Somebody had to design that track hoe to work, to support the load. Dirt's heavy. It's way out there in that bucket as it's about to dump. How does that all work? That's what we look at when we look at the statics of that machine. How are frames and machines different? Well, frames are usually not designed to move. Think of them as the stationary structures, like for instance, the white components here of this roller coaster, the frame of the roller coaster. Even some of the red part here, just not the coaster itself, that would be the applied load, but this coaster here has to be designed to withstand the loads that are imparted on it by the coaster. Machines contain moving parts and are designed to perform useful work for us. So what are the strategies for solving frames and machines? Well, they are more complicated than trusses. Trusses, you had method of joints, you had method of sections, you had the two-force member bit, yada, yada, yada. Frames and machines are a little bit more open-ended. They're a little bit harder to solve because they're just more general in their nature. So these are more, strategies necessarily than just like a solution, the steps, okay? This is more of a strategy. Hints and tips on how to succeed with frames and machines. Like usual, if you can solve for external reactions from just the overall structure, that's probably advisable. Go ahead and do that. Because if you cut a free body diagram and it has those reactions on there and you have not solved for them, that free body diagram is not going to be useful because all you're going to be doing is opening up a whole can of worms, a lot more unknown vectors whenever you make a cut. Do look for any two force members that you have in your structure. Just because it's a frame or a machine doesn't mean there aren't any two force members in it. Remember, their definition is that they have at least one multi-force member in it. So, for instance, in that track hoe that we were looking at, it has hydraulic jacks that run the arm. Each of those hydraulic jacks would be a two-force member. It's either going to have compression or tension on it. So that will simplify your world if you can recognize those two-force members. If you can't solve for the reactions up front because there are too many, and we'll see that in one of the examples that will work for, I think, the machine example for this module, then you need to look for an internal something. And here I'm saying a hinge. It could also be a cable, like we'll see in the example I'm going to do. If you see an internal hinge like you would at each end of a hydraulic jack, you have that two-force member. You also know that there's no moment acting around that hinge. There's no moment transferred by that hinge. That's kind of the definition of a hinge, right? Is instead of it resisting rotation, it allows rotation. It is a moment release. So if you can see those things, that's usually where you want to go. And you can draw a free body diagram with a cut at that location. And that will help you solve for some of those reactions that are on the external structure, because that's a known internal state, and it'll help you dive into the structure that was otherwise had too many unknowns for you to solve. Once you have some of those reactions, you can go back to your overall structure and solve for the remaining reactions. And remember, these types of problems are often going to be tougher than trusses. Just doing a bunch of practice would help you. And remember to always draw just really good free body diagrams.